Thank you very much for coming, and welcome to the Newgate Redleaf Artificial Intelligence Conference. For those of you who are slightly confused by the name change from our recent electric vehicles conference, we are in the process of combining with Newgate Communications, which gives us a much improved offering, a broader skill set and greater scale, such as we now have over 50 listed clients and are one of the largest agencies in the UK. However, back to the conference at hand. So we are delighted to see so many of you here for what I hope will be a fascinating debate and insight into how artificial intelligence will play an increasing part in business, the workforce, and of course, investment portfolios. Today's conference will cover a wide range of topics, including machine learning, cybersecurity, Internet of Things, neural machine translation, natural language processing, the future of work in cities in the UK, and a look at M&A in the sector. Sundar Pichai, I believe that's how you pronounce it, the CEO of Google, recently stated that AI would have a greater impact on the world than the exploitation of fire or electricity. Advances in AI and robotics are powering what many believe to be the fourth industrial revolution, or more accurately, the third technological revolution. Artificial intelligence itself is not a new phenomenon. In 1956, academic researchers were looking for a way to imbue machines with a human-like general intelligence, including complex reasoning. Some believe that this remains a distant aspiration, although as you will see today, I hope, it might now be closer than we think. Gurdeep Singh of Microsoft has described AI systems as idiots savants. They can easily do jobs that humans find mind-boggling, such as detecting tiny flaws in manufactured goods, but have trouble with things that people find easy, such as basic reasoning. What is most interesting now is that investment into AI grew by 50% in the last year. A separate study by Cognition X, in partnership with the Mayor of London, revealed AI represented approximately 10% of all tech raises in the city in 2017. M&A is therefore going to be an increasingly important factor as this sector grows in size and relevance. Okay, and without further ado, I'd like to hand over to our first speaker. James is the Global Head of Products and Solutions for KX, and he is going to speak on machine learning, the growth of predictive analytics.
Great, thanks very much, Ralph. So my name is James Corcoran. I run Product and Solution Engineering at KX, and it's a pleasure to be here this morning. My job is to talk about machine learning, and specifically our growth strategy around machine learning as a subset of AI. So I'll quickly introduce our company before we go into the heart of the presentation. So I work for KX. We are a subsidiary of First Derivatives PLC. We were founded about 22 years ago, and we're listed on the London Stock Exchange. We're about £1 billion in market cap and close to 2,500 employees. Offices all around the globe, and really what we're most well known for is processing huge quantities of data. Specifically time series data, data which is structured and needs to be analysed very, very fast. We've got a rich heritage in capital markets, deploying this technology in areas such as electronic trading, and I'll talk about some of the use cases for KX technology. But our strategy with predictive analytics and machine learning is helping us to grow outside of capital markets, and so I'm going to give you a little bit of context about what we think machine learning and predictive analytics is, how it can be used, but really I want to focus on some of the real-world use cases that we're working on today. So first of all, what is predictive analytics? Well, we very much see it as the fourth pillar, I guess, of what we sometimes call a data pipeline. So the first pillar there is data, which is effectively information about your business. So most businesses collect data, and then most businesses do reporting on that data. So reporting, quite simply, is querying that data, querying the information to figure out what happened and why did it happen. And then you move on to monitoring, which goes from a historical type of analysis to a real-time analysis. So monitoring is querying your data, but your real-time data to figure out what is happening right now, which brings us to predictive analytics, the fourth pillar. We define predictive analytics as what might happen in the future, and the word might there is important, because predictive analytics for us is not what will happen, but what might happen. So that's our definition. And the next 3 points kind of flow on from that. They're consequences of that definition. So for us, a predictive analytic should always include confidence results. So that means if you are predicting something, you should give a probability based on that outcome. So scenario XYZ might happen with a confidence interval of 85%, for example. Predictive analytics should also allow for what-if scenarios. So if X happens, what happens variable Y? So this classic what-if type of scenario analysis. And it should always give alternatives. So yes, you should talk about what might happen in the future, but you should also talk about if that doesn't happen, what else could happen. How long has predictive analytics been around? A very, very long time, we think. This is a picture of a man called Thales of Miletus. He was born in 624 BC, and he was regarded by Aristotle as one of the first great Greek philosophers. But he was also a mathematician, and one of the famous stories about this guy is that he predicted a bumper crop growth for olives in his region around 610 BC. And he used that by analyzing weather data and data about astronomy data, because he's also an astronomer. And so he predicted this bumper yield for the next year. And he went around to all the carpenters in the region, and he paid a premium to the carpenters to have the first right of refusal to use their olive presses. And so next year came along, there was indeed a bumper yield for olives, and he was able to leverage the use of those olive presses and sell access to those presses at a massive premium. So the story goes that he's the first guy to use predictive analytics, and he's also the first guy to create and subsequently buy an options contract. So how does it work? Well, very simply, you can think of predictive analytics as taking a set of data and using mathematical or statistical techniques to predict outcomes using that data. There's not much more to it than that. Well, how will it work in the future? When you take that paradigm, you have a set of data or many sets of data, and you want to use mathematical and statistical techniques to predict outcomes. Machine learning is one technique that you can use to predict those outcomes. So we see machine learning as a subset of predictive analytics, as a subset of a broader topic called AI. So a little bit about the hype cycle associated with all of these types of terms. Artificial intelligence, deep learning, machine learning, predictive analytics, data science, they're all interrelated terms, they're all interrelated disciplines in the market. The temperature gauge there, the size of it or the height of it, represents the number of times these terms were referenced in articles on the internet, I think in the last 12 months. So artificial intelligence is a big one. You can see machine learning slightly less so referenced. Data science is on the way down, but still referenced quite heavily. Cognitive computing is on the way. So we think the cognitive computing, there's going to be a massive hype associated with it. It will be deployed. And really cognitive computing is all about using, modeling your mathematics and your statistics based on how the brain works. So there's a huge hype cycle coming with cognitive computing, but with every hype event, there are dangers and warnings. Specifically with cognitive computing, IBM Watson, for example, this is referenced quite heavily in the public domain. IBM Watson versus cancer, there was a lot of talk and hype about how cognitive computing could be used to cure cancer, to the point where you had consultants and engineers showing up in wards to collect data and to do analysis and to do trials. And patients were asking, oh, is this the guy coming to cure my cancer? So it's a dangerous example of what can happen when there's too much hype associated with something that is not fully implemented or fully understood yet. Another example is predictive bias. So this is where you might use emoticons or a chatbot. Someone here has used an emoticon of a gun, and the predicted emoticons to use next are things like knives and a man with a turban. So again, examples of machine learning techniques which, if not implemented correctly, can make the world a worse place as opposed to making it better off. So it's very, very important to understand these techniques and to use them properly. So to define machine learning at a high level, compare it to traditional programming where you have data and you have a software program. You put that combination of things into a computer and you get an output. It's pretty deterministic, it's statistical, it's rules-based, and it's easy to get an output using a combination of data and software. Machine learning, on the other hand, just kind of flips those variables around. So again, you have data, but you also feed in the output. So this is the data that was recorded, and this is the output as a result of that data. You feed that into a computer, and out comes the program. And that program can then be used to predict events based on new data that arrives. So it's a different paradigm for programming. What isn't machine learning by comparison? Well, it's not statistics per se. It's certainly not easy to implement. It's not fast either in terms of computing. Sometimes these things take a long, long time to model. And it's not something where you can just throw data at it and expect a reasonable answer. So to dive into it a little bit more, broadly speaking, machine learning you can categorize into unsupervised learning and supervised learning. So unsupervised learning is where you group and interpret data based on input data only. And then supervised learning is where you combine data and the output of that data to train the model. And broadly speaking, then, they can be categorized as clustering techniques, classification, or regression. So clustering is where you are grouping things which are similar together. You don't typically have hard boundaries. You're just saying that these objects are similar to each other. So similar customers in retail, these customers tend to like buying bananas, for example, in these months. Classification is where you do have hard lines between your variables or your objects. So you're defining, okay, well, I'm going to classify this group of objects with this label, and I'm going to give a different label to another set of objects. And then regression is more numeric. So regression is basically assigning a number to a future event. So given this set of numbers or this trend in data, we predict that the next number is going to be X, Y, Z. Okay, so with that context, I want to give you some real-world examples of where machine learning and predictive analytics is being used, we think, at the forefront of a lot of the innovation that we're seeing in the market. Many of these examples are projects that we, as a company, are working on with our customers. And the first one is in high-tech manufacturing. So this is a massive industry with heavy-duty machinery, which costs tens of millions of dollars per machine. And our customers are typically manufacturing things like plastic objects, things like hard drives, things like chipsets, etc. And there are many, many variables or many inputs that go into these machines to make the devices or the objects that they need to create. And if one of these machines fails, or if one of the machines is configured incorrectly, you might be trying to produce a batch of 10,000 plastic devices, for example, and that batch could be rendered completely useless, or that batch might have 60% quality, or you might have to throw out some of the results. And these are expensive mistakes to make. And so what most of the manufacturers have done in the world's biggest manufacturing companies is create these machines which have hundreds, sometimes thousands of sensors on the machines. And the sensors are monitoring every single thing that goes in and every single thing that comes out. So they're monitoring things like the temperature, signal gauge, colors of spray paints, literally hundreds and hundreds of variables. And they monitor it, sub-second. So they might monitor an event 100 times a second or 1,000 times a second if there's high frequency signal generation involved. And we can hook up to those sensors, take those streams of data and use predictive analytics to predict whether a batch is going to be good or bad. So you can do things like predictive maintenance on the machine, predict if the machine is going to fail, and take preventive action before an event like that happens. And then you can also, more so than a human being could figure out how do I reconfigure this machine for the optimal batch performance? You can have our technology automatically change the settings on those machines. So that's a really powerful example, we think, of where machine learning is being used in a very, very practical sense with payoffs plus and minus in tens of millions of dollars. The second example we want to talk about is a project actually that Google are working on. These are pictures of a cornea. And what Google have done is they've taken pictures of, I think it's 300,000 patients and used the analysis of the cornea to predict heart risk or the risk of a heart attack over the subsequent, I think it's 5 years. The default test for heart risk or risk of heart failure over a 5-year period is a blood test, and a blood test is usually, I think it's 72% accurate. Using 300,000 patients and analyzing specifically the veins and the thickness of the veins in the cornea, Google have been able to train a model which is 70% accurate. So it's thereabouts in comparison to a blood test, and that's using 300,000 patients as a sample. So you add more patients, you add more data, you add more analysis, and this is likely to overtake blood tests in the future for heart risk tests. Related to that, this is an interesting one, a company called Babylon. This was on the BBC News, I think, last week. Babylon have done something really, really interesting with machine learning. They partnered with doctors in the UK, and they've taken all of the notes associated with doctors that they write down from their patients. And they've also taken the results of courses of treatment. And they've used it to create a bot, effectively, which can be accessed online, which allows you to type in your symptoms, and this machine will suggest a course of action. Again, this is, I think it's 75% accurate. I think the official statistic, doctors in the UK, they're about 85% accurate when it comes to diagnosis and suggestive courses of treatment. But the really interesting thing here is not the average performance, it's the variance of that performance. So doctors have roughly an 85% accuracy, but that's a variance of sort of 45% to 92%. And that's a problem if you're a patient, because you're relying almost on luck in some cases. So you get a much more kind of rounded, consistent performance with the machine here, with an average of 82% all of the time. Okay, the third real-world example of where we are employing machine learning techniques is in surveillance and compliance within capital markets. For many, many years, the banks have been regulated heavily. They have to improve their trade surveillance systems, their compliance systems. So they have to monitor their own traders for things like attempted market manipulation, insider trading, front running, all of these predatory type of practices. And our software traditionally has used statistical rules-based engineering to monitor for these types of events. So we're looking at streams of data. We're saying, well, if this happens, then do this piece of analysis. And then if that happens, then this is potentially an attempt to manipulate the market. Using machine learning, we can go from a rules-based system where you have to almost think about things up front to a more predictive model where we can analyze data, events, behaviors from traders, and mainly the use case here is to reduce the number of false positive alerts that you generate. So when it comes to machine learning, a lot of people ask, well, how do you do it? How does an organization implement machine learning? We advise to approach it like any business process re-engineering. So there's 3 reasons why you would engage in a machine learning project: cost savings, revenue generation, or revenue protection. There's really no point in saying, okay, I'm going to do machine learning if you don't have a problem to solve, and specifically if you don't have a problem to solve, which falls into one of those 3 categories. And then the next question is, well, do I need big data to employ engineering? The answer is it depends, but usually not, actually, because if you think about organizations today, organizations and businesses make decisions based on data that they have available. Of course they do. And so you can improve those decisions based on the data that you have. You don't have to start collecting additional data. That can come later. But usually you have the data already available, so you can employ machine learning techniques without having to embark on a massive big data project. And then modeling is the 3rd component. Machine learning is not like starting a traditional IT development project. It doesn't really have a start date and an end date with very specified requirements up front handed off to a development team. And this is a much more iterative process. And the modeling kind of looks like this. So first of all, you've got to get the data, you've got to acquire it, you've got to put it into a database, whether that's real-time data or historical data. And then you've got to clean, prepare, and manipulate the data. So this is the bit that a lot of data scientists spend way too much time doing. So techniques are improving here to, we call this feature engineering as well, to prepare the data for modeling. And then you've got to train the model. So you've got supervised and unsupervised learning. You've got to train that model to get the program out of the computer. And then you have to do a whole load of testing. So you got to test the data. You got to make sure that there's no things like bias prediction in there as well. And then there's a constant improvement cycle. And this is why we say it's iterative, because when you get to the 5th step, you go back to the 1st step. So you're constantly feeding more data in, you're constantly retraining your model, and that's how machine learning techniques get better, and it's also how your predictive analytics get better. So that covers the presentation, what we wanted to talk about today. So machine learning is a technique that can be used within predictive analytics, which is a subset of AI. And for us, at least, in KX, machine learning and predictive analytics is absolutely a massive part of our growth strategy as we deploy software solutions within capital markets and beyond. So thank you very much.
Thank you, James. Any questions from the floor? Yes?
Thank you, Smart. James from Liberum. How do you make money? Can you talk through your sort of revenue model and whether, for instance, you can bring a contingent element into in terms of costs saved, etc.?
Yes. So how do we make money, or how do our clients make money?
How do you make money?
Yeah. So we are a PLC. We've got 2 practices. We've got a consulting practice and a software practice. I work in the software practice, which is KX, and we license technology to our clients.
I suppose what I was thinking was whether, if and when you can demonstrate costs saved for your clients, like the factory one, are you able to strike contingent deals? Would you strike a contingent deal where you can sort of agree a baseline and then get paid on a percentage of cost savings? What's that?
Our default licensing model is that we license our core technology, which gives you a capability, and then we engage in a project which has a business outcome that we need to achieve. So contingency then could be baked into one or other, but our core business model is licensing of software, which is our database technology, and then we use machine learning techniques on a professional services basis.
Could you talk a little bit about the infrastructure that you use, the hardware that you use, whether it's cloud, and then also as you move from training to inference or implementation, how that hardware kind of changes, please?
Yeah, sure. So for a long time, we were running on sort of commodity servers. So everything from a laptop to a big Intel server. More and more so these days, where we're deploying in the cloud, obviously, like everyone else. We tend to run hybrid architectures on behalf of our clients. So what happens is if you've got really low latency, high performance requirements, usually you want to deploy that onto a server which is either sitting here or in capital markets, you're co-locating with an exchange. When we deploy to the cloud, usually the use case is you want burst computing. So you want to be able to spin up some instances in the cloud, and that typically is for training the model. Sort of as a transient event, you can ship data to the cloud, you can run some models, and you can spin that down. And then once the models are trained, you can deploy those back to your in-prem data centers. As part of sort of a broader movement, we see most things going to the cloud. The cloud, most of the big cloud vendors we're partners with the big three, have really good options now for low latency, high performance, which is something that was missing in the past.
And then just in terms of the physical hardware, are you doing the training on GPUs and then spinning to TPUs and ASICs? Or?
It's a combination. It depends on the model. We're by default a CPU database. When it comes to the training specifically, if you've got something that's highly parallelizable, you can employ GPUs or TPUs are becoming more and more popular for sure. So we've interfaces with all of those things where you can sort of combine the best of both worlds, because with large volumes of data, what you typically want to do is CPUs are better for that. And then the training, if it's highly atomic, you want to offload to TPUs. So we've got interfaces to all of the above.
Accepting that humans make mistakes, you said that predictive analytics is about 85% accurate. So the question is that enough? And who takes responsibility for the 15%?
It's a good question. I think it's quite dependent on the environment or where that specific solution has been deployed. You can, in general, the more data you have, the more training you do on a model, the better it gets at prediction. There is such a thing as overtraining, which leads you to have too narrow a focus, which is a problem. But in general, the more data you put into the model, the better your prediction can be. In terms of who is responsible for it, I mean, this is something that is engaging the legal industry at the moment in a big way. I mean, a big example would be autonomous vehicles, right? So, when an autonomous vehicle kills someone, who's responsible? And that's a question that is not answered today. But we think fully autonomous systems are rarely used today. So machine learning is usually a technique that helps a human being either interpret it before, so that a human can make a decision, or at least monitor what's happening as the machine's making those decisions.
You showed a few examples. A lot of them included structured data in machine learning and predictive analytics. How far are we from using unstructured data, and how does your software cope with that? Thanks.
Sure. So unstructured data is a little bit more challenging, and there's some extra techniques that you have to employ to firstly analyze that and prepare it for training and for machine learning. So a good example of that is text-based data. It's usually pretty unstructured. So you can use natural language processing, and there are many open source libraries out there that help with natural language processing, which effectively takes a set of unstructured data and sort of classifies it in some way, groups it, aggregates it, and allows you to apply labels, which then can be fed into models. it's the combination of sort of structured and unstructured data is where you probably have the highest business benefit. And our software, up until maybe sort of 4 or 5 years ago, was predominantly used for structured data, but we recognized the trend towards unstructured data and the benefit of combining those two types of data could bring. So we've modified and enhanced our software to be able to cope with unstructured data.
Thank you, James. I'm going to stop it there on him, but I'm sure there'll be opportunity to ask some questions in the break.